Within this module, we have looked at the birth and life of stars. We have explored the stellar nurseries and discovered that stars, just like humans, walk different paths. Yes, we all eat, sleep and explore life, or, in the case of a star, burn fuel and shine bright. However, just as there are different paces of life for us humans, so too can stars live and die in many different ways. Now that we know the basics, let's explore the life of rock stars and that of average Joes. In the stellar sense, that is. Let's see how different stars move towards the end of their lives. Here we will discover that the life and subsequent death of a star are determined at birth by the star's mass. But how can this be the case? The story of a star's death begins at the point at which it leaves the safety and security of the main sequence. The main sequence is the long main track observed in the Hertzsprung-Russell diagram. We have learned that stars seen in the upper left of this track burn hot, blue, and are massive, weighing 10 to 100 times the mass of our Sun, or possibly more. Stars at the lower right of the track are cool by stellar standards. They are red and may only contain 1/10 of the mass of our Sun. We have also learned that blue stars tend to be called high mass, while stars like our Sun and smaller are often called low mass stars. When a star leaves the main sequence of the Hertzsprung-Russell diagram, the star is seen to move towards the right of this plot. This movement is the result of the star becoming redder. But what does this change in colour represent? What changes in the star's interior are powering this shift? And what happens in the time between the departure from the main sequence and the star's demise? This is what we are about to explore. When a star's core runs out of hydrogen fuel, the core can no longer sustain the outward radiation force that balances the force of gravity which is pulling everything inwards. Therefore, the star will no longer be in hydrostatic equilibrium. This loss of radiation pressure results in the star's core collapsing. The collapse of the core, in turn, causes the temperature of the interior to increase. When a star burning primarily hydrogen suffers from such a collapse, it will contract until the core reaches about 100 million degrees. At that temperature, the star can begin to burn helium in its core. Helium will become the main source of energy for the star at this point, as it fuses to create carbon and other trace elements. However, if we look just outside the helium core, we can see that the core is surrounded by a shell of hydrogen that is also burning. This hydrogen shell is slowly consuming more material as it moves outward through the star. As the helium burns hotter than its predecessor, the hydrogen core, it burns more rapidly. Therefore, this phase of the star's life is shorter. Once the helium core is exhausted, the core will once again collapse. As it collapses, the temperature will once again increase. If the collapse leads to a temperature of 600 million degrees, the star is able to burn carbon. Such a core would be surrounded by both helium and hydrogen shells. Once the carbon burning is complete, the cycle can again repeat, leading to neon, oxygen, and even silicon burning, with the core becoming heavier and heavier. As each layer is hotter than the last, the star burns through the core more rapidly. For example, a star could take billions of years to burn through its hydrogen, whilst it may only take hundreds of years to feed on a carbon core. By the time we reach silicon, it's possible for a star to consume its core in about a day. The multiple layers of a star seen here have led to these stars sometimes gaining the nickname of onion stars, as onions have layers, just like ogres, or cakes, or parfaits. Everybody likes parfaits. Where was I? Back to stars. Yes, they have layers. Okay, but it all stops with iron. When learning about fusion and fission, we discovered that the most tightly bound atom is iron. and that no more energy can be gained by either breaking iron apart or by smashing two iron nuclei together. As a result, there is no fuel left for the star to burn through. Fusion in the core must stop, and the star will die. We will explore more of the death of stars in the next two videos. Meanwhile, so far we have been looking at what's going on inside the star. But what effect does that have on the outside of the star? Or rather, what effect does that have on what we can see? When stars run out of the current fuel in their core, we discovered that the cores collapse. This continues until the star is able to burn a new type of fuel. So for example, when a star initially runs out of hydrogen, it will collapse until the helium fires begin to burn. What effect does this have on the envelope of the star? The envelope is the outer hydrogen-rich region of the star which is not involved in nuclear fusion. It is the outer layer of the star. Well, as the core collapses, the energy generated by this collapse drives the diffuse envelope outwards, and so the star expands. As it becomes less dense, it cools, and so it reddens. This means that we would see the star appear to grow in size while becoming redder. If we return to the Hertzsprung-Russell diagram, we will see that this means that the star leaves the main sequence and becomes either a red giant or a supergiant. This expansion and reddening happens each time the core runs out of fuel and searches for a new source of food. As a result, the stars can move great distances from the main sequence over time. However, as a star lives most of its life on the main sequence, it is the loss of hydrogen in the star's core that is the easiest to mark. A star's departure from the main sequence is known as the star's turn-off. What kind of size difference would we expect to see though? Well, in the case of our Sun, we would expect that the surface of the Sun would reach out and swallow up the Earth, possibly even extending out to Mars. We don't need to worry though. We have about 5 billion years before this is going to happen, so we have a little more time to crack the problem of space travel and venture out to explore the universe before our Sun dies. You never know, we might come back to watch the death of our Sun on the day 5.5/Apple/26, as they did on Platform 1 in the Doctor Who episode, The End of the World. So what about stars other than our Sun? How will their mass affect their lifespan? How will their life and their lifespan be affected by the fuel they burn? If we start by considering the life of an average Joe, that is to say a low-mass star, they can spend 10 to 100 billion years on the main sequence, slowly burning through their hydrogen cores. At the end of this time, they will depart the main sequence, obtaining their middle age spread, before puffing up to become red giants. In this phase of a low-mass star's life, an average Joe will carry on, plodding along as it slowly consumes its helium core. At this point, the core will collapse, but will never reach a temperature that is hot enough to ignite its carbon fires. The star will instead end its life quietly, missed only by its family of planets and its close friends. But what about the rock stars, the high-mass stars? What path do these stars take? High-mass stars, like many well-known rock stars, live fast and die young, in a huge explosion. Explosions so massive that they can be witnessed in other galaxies. The rock stars in the stellar nursery are more massive and so contain more hydrogen, but they are also much hotter. High-mass stars burn through their hydrogen cores at a much faster rate, departing the main sequence after only maybe 1 million years. At this point, the high-mass star will switch to burning helium, then carbon, and so on, building up multiple layers. The number of layers the onion star builds up depends on its initial mass. The more massive the star was at its birth, the closer it can get to an iron core. During this time, our rock star will go through a giant and possibly even a supergiant phase as the outer envelope swells, before a rock star eventually dies. The explosive nature of our rock star's ending is explored in more detail later in this module. Our average Joes and our rock stars were all born in the same stellar nursery. These stars were all born around the same time and yet live very different lives at very different paces. By taking measurements of stars to obtain their colour and brightness, we are able to learn more about where the star is in its life cycle. However, we can also use this information to find out about the stars that came from the same nursery. If we take measurements of lots of stars from any given cluster, and when I say cluster, I mean all the nursery graduates that are still around, we can create a Hertzsprung-Russell diagram for that cluster. This will provide us with a clear view of the current turn-off in the main sequence within that cluster. If we check what types of stars are currently turning off, we are able to determine how long they would have been living on their diet of hydrogen in their cores. This will tell us the age of the cluster. By taking the measurements of multiple stars, we can tell if this was the graduating class of 100 million, a billion, or even 10 billion years ago. If a cluster is still very blue, then it must be young, while a redder cluster will be old. Clusters of stars change colour with age, just as stars do. The hotter, bluer stars die out first, then the average stars, and finally the red dwarfs. Eventually, all stars die off, resulting in the production of elements that can feed into the next generation of stars. This stellar death is the next avenue to be explored in our journey through the life and death of a star.